In this video, I'm going to talk about the integral test. We'll learn what it is, why it works, and we'll do some examples on it as well. There are two forms of the integral test. There's an integral test for convergence and there's an integral test for divergence. First of all, we're going to focus on the integral test for divergence because the why it works is a little bit easier to understand. But first, let's talk about what the integral test for divergence tells us. It tells us that if f is a positive, continuous, and strictly decreasing function, then the series, the infinite sum, of f evaluated at the natural numbers 1 up to infinity, that diverges if the integral of f on the interval from 1 to infinity also diverges. This is useful because the integral of a function is often easier to compute than the series of a function, and if we can show that the integral diverges, then we know that the series diverges. So when faced with the difficult problem of telling whether a series diverges, we can use the integral test for divergence to transform that into an easier problem of telling whether an integral diverges. To see why the integral test for divergence works, it's easiest to think about the series and the integral in terms of area. For starters, let's look at this graph. Here we've got a graph of f of x as a curve, and we've also got some rectangles which have height f of 1, f of 2, f of 3, f of 4, and so on. Since all of the rectangles rise above the curve, we can see that the area under the curve is smaller than the area of the rectangles. Now, the area under the curve is just given by our integral here. That's the integral from 1 to infinity of our function, of our curve here. So we can just substitute that in here. And the area of the rectangles, well, each rectangle is base times height, and the base of each rectangle is 1, and the heights are f of 1, f of 2, f of 3, f of 4, and so on. So we just got 1 times f of 1, plus 1 times f of 2, plus 1 times f of 3, plus so on. Well, that's just our sum of f of 1 plus f of 2 plus f of 3, f of n for all of the natural numbers, n equals 1 to infinity. So we can substitute that in, and we have this inequality here. Now, if the integral diverges, then the left-hand side of this inequality goes to infinity. Integral diverges just means it blows up to infinity. And if infinity is less than our series here, then our series also has to be infinite, which means the series also diverges. So to recap, the series always has to be bigger than the integral. So if the integral diverges to infinity, the series has to follow suit. Let's use the integral test to show that this series diverges. The integral test just tells us that the series of this function, 1 over n plus 4, that diverges provided the integral of the continuous version of that function also diverges. But before we get into computing the integral and showing it diverges, let's make sure that this function 1 over x plus 4 actually satisfies the assumptions of the integral test. If it doesn't satisfy these assumptions, then the integral test is really of no use to us because it doesn't apply to the series. So let's make sure that it satisfies the assumptions before we go through all the work of computing the integral. First of all, is this function positive? Well, we're doing 1 divided by the quantity x plus 4, and x is on the domain from 1 to infinity. So x is a positive number, and a positive number plus 4 is a positive number, and then 1 divided by a positive number is a positive number. So yeah, the function is always positive. Great. Now, is this function continuous? Well, the only problem with continuity would be if the denominator goes to 0. And the denominator goes to 0 when x is negative 4. But negative 4 isn't in the domain we're interested in. We're only interested in x on the domain from 1 to infinity. That's what our integral is, that's what our series is. So on this domain of 1 to infinity, our function is continuous. The only discontinuity problem happens outside of our domain. So we're all good. Lastly, is the function strictly decreasing on our domain? Well, we're doing 1 divided by x plus 4, and x is increasing, so x plus 4 is increasing, so the denominator is increasing and the numerator is staying the same. But that's just dividing a number by a progressively bigger denominator, which results in a smaller and smaller result. As the denominator gets bigger, the overall result gets smaller and smaller. So yeah, the function is strictly decreasing. Great, so we've satisfied all the assumptions of the integral test, and we can go ahead and compute our integral, and provided the integral diverges, we know that the series diverges. So computing the integral, this is really a limit. It's the limit as the upper bound b goes to infinity of that integral from 1 to b of 1 over x plus 4 dx. Now this integral is just a natural log integral. This integral just comes out to natural log of x plus 4, and that's going to be evaluated at the bounds 1 and b, and we're still taking the limit as b goes to infinity. So let's go ahead and evaluate this at the bounds. We'll put our limit in front, limit as b goes to infinity of, well, natural log of x plus 4 evaluated at b is just natural log of b plus 4, and then minus natural log of x plus 4 evaluated at 1, which is just natural log of 1 plus 4, which is 5. Alright, so now we can just compute the limit, and we just need to split up the limit over the two terms. So let's do that. Limit as b goes to infinity of natural log of b plus 4, and then minus, well, this term doesn't have any b in it, so this just, the limit of this term is just ln of 5. Alright, so now this term here, limit as b goes to infinity of natural log of b plus 4. That makes the inside argument here, b plus 4, that goes to infinity, and as the inside argument gets bigger and bigger, natural log gets bigger and bigger. So this limit here is really just infinity. And when we subtract a finite number, ln 5, from infinity, we still end up with infinity. So yeah, the integral diverges, so therefore the series diverges. Now let's take a look at the integral test for convergence. So this is a very similar concept. If f is a positive, continuous, strictly decreasing function, then the series converges if the integral converges. So same idea as the integral test for divergence, same conditions, same series, same integral, except if the integral converges, then the series also converges. The test for convergence works in a similar way that the test for divergence works. We start off by thinking about a graph with some areas labeled. Here we've got our function f of x, that's our curve, and we've got some rectangles that rise up to heights f of 1, f of 2, f of 3, f of 4, and so on, just like last time. And we see that if we start off with the area of the first rectangle and then add the area under the curve, then that area is going to be more than if we added all the other rectangles, because the rectangles are all under the curve. In other words, the curve has more area than the tail end of the rectangles. So we can set up an inequality, the area of this first rectangle plus the area under the curve from 1 to infinity is bigger than the area of all the rectangles. And we just substitute here, area of first rectangle, that's just base is 1 times height f of 1. And then area under curve, well, that's just the integral like we saw previously. And the area of the rectangles, well, same idea as before, that's just base times height for all of them, and that turns out to be the series of f of n from n equals 1 to infinity. So we've got this nice inequality here, and so say that the integral converges. Suppose it converges, then the integral comes out to a finite number, and we've got that f of 1 plus some finite number is bigger than the series. Now, if we have a finite number and then we add f of 1, which is another finite number, then we get a larger but still finite number. So that means that the series is less than some larger but still finite number. Well, the series is just less than a finite number, and that means the series also converges. If a positive series is less than a finite number, then it has to be a finite number itself. Let's apply the integral test to show that this series 1 over n cubed converges. So the integral test just tells us that to check whether the series converges, we just need to check whether the integral converges. But before we get into that, again, we need to check the assumptions of the integral test. We need to make sure that this function is positive, continuous, and strictly decreasing. Otherwise, the integral test is useless and there's no point in computing the integral. So first of all, is the function positive? Well, in the domain that we're interested in, x goes from 1 to infinity, so x is a positive number, and a positive number cubed is still a positive number, and then 1 divided by a positive number is still a positive number. So yeah, it is positive. Is it continuous? Well, the only continuity problem happens when the denominator goes to 0, which happens when x is 0. But we're only interested in x going from 1 to infinity, and 0 isn't included in that domain. So we don't have any problems with continuity. Great. Lastly, is our function strictly decreasing? Well, as x gets bigger and bigger, the denominator x cubed gets bigger and bigger, and 1 over a bigger and bigger denominator results in a smaller and smaller fraction, so yeah, our function is strictly decreasing. Now we're good to go ahead and compute our integral. We want to show that it converges, just meaning we want to show that its result is a finite number. So let's go ahead and compute this. Again, this integral is really just a limit from 1 to the upper bound b, so let's put a limit as b goes to infinity in front, and then the inside 1 over x to the third dx. Now this integral here, integral of 1 over x to the third, that's just negative 1 over 2x squared, and we want to evaluate that at our bounds, 1 and b, and also take the limit as b goes to infinity. Okay, so let's write our limit as b goes to infinity and evaluate it at our bounds. So evaluated at bound b, we have negative 1 over 2b squared, and then evaluated at 1, we're subtracting negative 1 over 2 times 1 squared, which is just negative 1 over 2. Okay, so here we've got a negative and another negative. A double negative just makes a positive, so let's change those to positive signs. And then we can go ahead and take our limit. Let's break it up. So limit of the first part, limit as b goes to infinity, of this term here, negative 1 over 2b squared, and then plus limit of the other term. Well, the other term is just a constant, so limit of that is just itself, 1/2. And the limit of this function here, as b goes to infinity, well, the denominator ends up going to infinity, and a constant divided by an infinitely large denominator is just 0. So negative 0, still 0, this ends up being 0. So 0 plus 1/2, and the result is just 1/2. So great, it is a finite number. That means the integral does converge, and that means since our function satisfied the assumptions of the integral test, then our series does converge. The integral test is just one of many tests that we can use to more easily establish the convergence or divergence of the series. In the future, we'll learn more such tests.